Okay, let's do some practice problems for Chapter 5 on 2x2 linear systems. Let's start by sort of going from a more verbal description into the mathematical algebra. So we're going to want to convert the matrix form to write down the linear system that finds the point 3, 0 in terms of the local coordinate system defined by the origin given by our two new vectors, 2, minus 3 for one of our basis vectors, and the other is 6, 0. So find this point in that space. We're actually going to do this 3 times or 4 times. First, we're going to do it by using Cramers Rule to solve the problem after we formulated it. Then we're going to use Gaussian Elimination without substitution, and then with substitution, and then finally we'll look at the inverse to solve that problem. Okay, so let's start with just trying to actually formulate it. Write down what is the matrix form of this problem. Have you got it? If not, pause until you do, but this should be pretty simple. We want to build our matrix form. We end up with a matrix 2, 6, minus 3, 0, right? We're going to take this basis vector as a column, this basis vector as a column, times x1, x2 equals our right-hand side. So this is the standard matrix equation for this verbal formulation. Now let's go ahead and solve that with Cramers Rule. So solve it with Cramers Rule and come back when you're ready. Okay, so with Cramers Rule, if I want to solve this system of equation, it's going to have the solution. I'm going to take the area of the determinant, or the area of the overall system. We get the determinant of 2, minus 3, 6, 0 on the bottom. And then on the top, we're going to have the determinant of getting rid of the odd items. So if we're doing x1, we take the second column and the right-hand side. We get 0, 3, replacing this column with the right-hand side, and 6. So the determinant of this is 3 times 0 minus 6 times 0. So the determinant is, of the top is 0, and we get 0. For the right-hand side, for the second item, x2, we do something similar. We leave the x1 column alone. We replace the x2 column with the right-hand side. So we get the determinant of 2, 3, minus 3, 0, which is 2 times 0 minus 3 times 3, so I get 9. And on the bottom, we're going to have the determinant of the overall system, so we get 2, 0, which is 0, minus 3 times 6, which is minus 18. So overall, I get 9 over 18, I get a half. So this gives us a solution 0, 1/2. Now, let's go solve the same thing using Gaussian elimination with no pivoting. So work through what are the forward elimination steps with a shear, and then what's your back substitution going to give you. Play the video after you've got your solution worked out. Okay, so now let's see if we come up with the same solutions. So our forward elimination, we want a shear to reduce this to upper triangular form, and we're not going to do pivoting here. So I need to find a shear matrix that when I multiply this makes this item go to 0. So that shear matrix turned out to be 1, 0, 3/2, 1. The 3/2 comes because we're going to take minus the value we're trying to annihilate divided by the item that we're going to leave there. So we take minus 3, gives us 3 divided by 2. And when we multiply that by the upper matrix, we get 2, 6, 0, 9. But we have to remember we're going to multiply both sides by our shear matrix. So on the right-hand side, our new matrix becomes 3 and 9/2. Now, we've described it here with shear matrices. You can also look at this just in terms of elementary row operations. So I can say this is replacing row 2 with row 2 times 3/2 plus row 1, which is really what this matrix is telling me. Multiply row 2 by row 1 by 1 and add to it 3/2 of row 2, and that's going to give me the item that's going to show up in this new location here. Okay, so now we do our back substitution. Right? We have our matrix here. We have 2, 6, 0, 9. We do our back substitution. We just divide both sides by half, and so we get x2 equals a half. Putting a half back in the top, we get 2x1 plus 6 over 2 equals 3. Subtracting 3 the other side, we get 2x2 equals 0. So x1 equals 0, x2 equals a half. We see that's the same answer as Cramers Rule. So now I want you to try it one more time with Gaussian elimination with pivoting this time, which is the way we should do Gaussian elimination on the computer. Okay, so again, 2 by 2, hopefully that was pretty quick for you. The first step is to do your pivot. So when you do your pivot, you swap these rows. Again, we're going to recite both left and right-hand sides. So now we get our system being minus 3, 0, x1, 0. 2, 6, x 2, 3. So that gives us our new system. And now we have one step of Gaussian elimination, one shear, to put this into triangular form. When we shear this one, it turns out that it's going to give us a diagonal matrix, so back substitution is very easy. We just divide through. 3 divided by 6 is 2. This one's just 0. So did you write down your shear matrix? The pivot point was easy, but shear is a little bit more complicated. In this case, our shear matrix is going to be 2/3. I want to annihilate the 2, so I'm going to take minus 2 divided by what I'm leaving, which is minus 3. So I get minus 2 divided by minus 3 is 2/3. So this is the shear matrix that when we multiply it by will give us this item. So the last way we could try and solve this is just because it's a 2 by 2 matrix, just write down what is the inverse. Okay, so if you've done this enough, you can write down the inverse, although on an exam you definitely want to write down showing some of your work. The inverse is this. The inverse can be found using the formula 1 over the determinant times d minus b minus ca. So if we had a, b, c, d, we swap the items across the diagonal and negate the ones on the off diagonal. And then the determinant is just 1 over a times d minus b times c. So that gives us our solution. We multiply all that out and we get our solution. I can then multiply the right-hand side by and get the answer. So since we're talking about inverses, let's try another inverse problem. Find the inverse of this matrix. Okay, hopefully you have your answer now. The solution to this can be done one of two ways. You can just use the formula we just did and try and figure out cosine 30 and sine 30 and work through a lot of algebra. Or you might notice that this is a rotation matrix. This is cosine alpha minus sine alpha, cosine alpha. So this is a 2 by 2 rotation matrix. And for rotation matrices, we know that their transpose is their inverse. So all I really have to do is replace sine alpha with minus sine alpha, and the sign just changes. So we just swap the signs here. The rotation by 30 degrees is the same. The inverse of rotation by 30 degrees is the rotation by minus 30 degrees, giving us our answer. So this one is a lot simpler than a general inverse. Now let's go to looking at kernels. What's the kernel of this matrix? Okay, hopefully you didn't have to look up what's a kernel. You could just look at this matrix and say, oh, look, I've got this row and this row are degenerate. They're multiples of each other, or this column and this column. So in fact, the kernel is the solution of this homogeneous system of equations, ax equals 0 or av equals 0. So for this matrix, that's all vectors of the form v1 equals minus 3 times v2, because this value here is 3 times that one. So for example, the value minus 3, 1 is a point in the kernel, and that gives us the kernel. We could normalize it so it's unit length, but in this case, we're just going to leave it as minus 3, 1, saying this is our kernel space or null space. One last problem, let's look at under and over determined systems. So give an example along with a sketch, give an example of sketch out an unsolvable system and do the same for an underdetermined system. So give us an overdetermined system, unsolvable, and an underdetermined system. Okay, so hopefully you remember that if it's underdetermined, in 2D, A1 and A2 means they're parallel, the matrix is singular, and in an underdetermined system, B lies on the same line as A1 and A2, so there's infinitely many combinations that'll give us the same value as B. Any combination of these two will give it, lots of combinations of these two values will give us B. For an overdetermined system, we again have a singular matrix, A1 and A2 are parallel, but B doesn't lie in the subspace formed by these. As we get to higher dimensions, under an overconstrained doesn't have to be that it lies on a line, it'll mean they lie in a lower dimensional subspace. A lower dimensional subspace of R2 is just R1, which is a line, but in higher dimensions it'll be more complicated. So underdetermined systems, even though the matrix is singular, has infinitely many solutions. Overdetermined systems, it's singular and there is no solution at all. So hopefully these problems were straightforward enough that you didn't have to look back at your book too much. If you did have to look back in your book, then you should try a couple more practice problems from the end of the chapter until you can do this by just looking at the problem or maybe looking at your notes.